We're going to go start to finish using the two-sided t-test in an example. There's a few steps to performing a t-test, and this is not the only way to break it down or frame it, but this is one good list that can help walk you through it. The first thing you're always going to do is start by defining your null and alternative hypotheses. This is the whole basis that your entire test is built on. So in an earlier example, we saw that this guy's fairway, the average fairway shot with a 3-wood goes 214 yards. Would he hit it a different distance with a 3-iron? Now in that situation, we defined the null as a statement of no change. So we said the null hypothesis is that the average distance stays the same with the new club, the 3-iron. So mu is equal to 214. The alternative hypothesis is that it changes. Now we don't know if it goes farther or shorter. Let's assume we don't know a whole lot about golf. We're not sure if this new club is going to make the ball go farther or shorter. And we're just going to say mu is not equal to 214. So exactly the same thing, just a not equal sign. So now we have our null and alternative hypotheses. Mu is equal to 214, mu is not equal to 214. Then we need to pick a threshold level called alpha. And what that means is we need to decide at what likelihood we are willing to say that the null hypothesis is in fact wrong. Alpha, that level, is the probability that you falsely reject the null hypothesis. So if this kind of error is really bad, like for example, if you reject the null hypothesis, and that would mean that someone could be put to death, or someone could receive a medical procedure that they don't need, or something like that, then you would want to make sure that alpha is a really, really small number, because it represents the probability that you're going to make that kind of mistake. When in doubt, you should always use the value 0.05, which is a 5% chance of making that kind of mistake. In most medical journals, in most papers of all kinds, in all different fields, 0.05 has kind of become this magic number for your alpha level. So if you don't have a particularly good reason to make it higher or lower, just go ahead and use 0.05 as your default assumption. Now, what that 0.05 represents is the tails of the normal curve. So if we assume that 214 is the middle of the normal distribution here, and these standard deviations came from values we're going to get later, so let's imagine we don't see those yet. What we're trying to do is figure out how likely it is that we could end up this far away as like 206 or 221.22. How likely is it that we could end up that far away from this null hypothesis? And if you add up the area in this tail and you add up the area in this tail together, it's going to be 0.05. That's what the alpha means. That you put those two areas together, you're going to get 0.05. So it represents how far away from the middle you have to be in order to get those results. So we set our threshold level, we set it to alpha as 0.05. Next thing we're going to do is we're going to collect some data in a sample. And we specifically said valid data because we want to make sure that we don't just go out and collect any information. It has to be done correctly. It has to be from an SRS. We have to have low response, non-response, all that kind of stuff. So let's imagine that after collecting an SRS of 30 shots, we found that we had a sample average of 207 yards and a standard deviation of 21 yards. So let's say this is the data that we collected. And as I was mentioning, we have to always remember to check for, one, that we had a good sampling technique. So in this case, it was an SRS. And it doesn't say anything about undercoverage or non-response. And two, you always have to make sure you end up with a normal curve. Now, the central limits theorem says that you don't have to start with a normal curve. You just have to start with something a little bit normal if you have a medium sample size, or you could start with almost any distribution if you have a large enough 30 to 40 in your sample. So with an SRS of 30 shots, as long as it doesn't seem like I'm going to have any super huge outliers in my golf shots, which let's assume that most of the shots were hits and they went a reasonable distance, a sample size of 30 should be enough to say, that's probably going to be normal. So we will assume that this distribution will be fairly normal with a sample size of 30. So now we have our data. We have our x bar 207, standard deviation of 21, our n is 30. We actually need to do the test. We need to perform the t-test and get our p-value. To find the t-test, you take out your TI-83 or 84, and you'd go to Stat, you'd go over to Tests, and you'd go down just one to t-test. Stat, Test, t-test. And the first thing you want to do is make sure that Stats is selected, not Data. You can make sure Stats is selected and hit Enter if it's not. And it'll ask you a few questions. The first one is, what is mu? And mu here is our null hypothesis, that's 214. Next, we have x bar. Now this is from the data. The next three are going to represent the data we've collected. So the first one, x bar, is going to be 207. Sx, our standard deviation, is going to be 21. And then n is going to be 30. And we just get that from our original problem. The next line here says, what is the alternative hypothesis? And what I found is the easiest way to do that is just look at whatever we have written on the paper and correspond that to these symbols. Now the not equals is pretty obvious. When you get into the greater than less than, it can be a little confusing to see what that means. So we'll practice that one later. And once you have all that typed in, you calculate. And what you're going to see here is you have a t statistic and a p-value. So let's drag that in. And here's what we now know. This p-value represents a certain probability. And so we're going to talk about what that actually is. If the null hypothesis were true, if we assume for a moment that mu really does equal 214, even though x bar is 207, let's go with mu equals 214. If we assume that were true, there would be a 0.078 probability, or a 7.8% chance, of getting a sample average as extreme as 207. There's this probability that our sample average is going to be that far away. It's going to be 7 away. It's not particularly likely. It's less than 10% likely, but more than 5%. So we end up in this value, and that's what the p-value is. Now you might say it's the probability that the null hypothesis is true. There's some specific reasons why that's not exactly an accurate statement, although it's on the right track. So I wouldn't say it that way. I would be careful to say, assuming that the null is true, assuming that mu equals 214, there is a 0.078 probability of getting a sample average, in this case, because it's not equals, as extreme or as far away from the mean as 207. Before we move on, I just want to mention the t-statistic up here, this negative 1.8. What that represents is effectively like a z-score. A t-score is pretty much the same as a z-score. It's how many standard deviations apart this value and this value are. I can show you on your calculator real quick. Since you just did your t-test and you did the calculate, at the bottom you'll notice there's another option for draw. If you were to push the draw button, what that's going to do, assuming you don't have too many other things plugged into your calculator, is draw this normal curve. And you can ignore those vertical lines there. That's just some other messes in my calculator. But what it's doing is it's shading those two ends in, and those two ends represent the p-value. So just as we colored in those two ends to represent alpha a moment ago, if you take this area plus this area all in black, it's going to equal this p equals 0.0782 as an area. And if you look at the t equals negative 1.8, if you go 1.8 standard deviations down and 1.8 standard deviations up, that's where you're going to see the area shaded in on the tails. That's where you're going to start shading in. The last thing you need to do is decide whether or not to reject your null hypothesis. So it says here that we got a p-value of 0.078. We have an alpha value of 0.05. All we do is compare these values. If P is greater than alpha, if P is bigger, we do not reject. That means that we do not have enough evidence to say that the null hypothesis is false. We compare those two, and all that we're saying is that we don't have enough evidence. We can't make the claim that mu is truly not equal to 214. Deep down inside, when I see a p-value under 10%, under 0.10, I'm thinking that, yeah, there probably is a difference. But again, I don't have enough evidence to really prove it. It has to be below whatever we set as our alpha. So if alpha is 5%, 0.05, then this p-value needs to be less than 5% to be able to truly reject the claim and feel good about it. So we failed to reject. That's unfortunate. That means our test did not prove what we wanted it to prove. So we're going to try another technique in just a moment using a one-sided test and see if that can make a difference.